This conference will now be recorded.
Hello students, we are continuing the POIQ discussions. 2nd September JEE Main Paper 20. Let us read this question. So the question says, the displacement time graph of a particle executing SHM is given in the figure. So T is missing here. The displacement time graph, you see this figure here, this is displacement time graph. It is a sketch, not to the scale. So this figure shows displacement time graph of a particle which is executing simple harmonic motion. Which of the following statements is or are true for this motion? So these are the options you see, like these are the points given for this particular figure, and these are the options we have to see. There are multiple points, like there are out of 4 there are more than one correct point related to this figure. We have to find out which of these 4 are correct, and according to that we have to choose the correct option in this question. Okay, look here, this figure. Before I read this points related to this figure, let me explain this figure a little bit. So you can see this is a kind of cosine curve, and you can see time starts from here. So this is t is equal to 0, here t is equal to t by 4, this is t by 2, this is 3t by 4, and here it is becoming t. That means this is actually a full of wave. Okay, you look, this is the full wave. A complete time period is this one. Complete time period. This is a complete wave. Okay, and also you see the time period is this much. Now this, at t is equal to 0, the displacement is maximum. That means amplitude is maximum. I'm sorry, displacement is maximum means it is the amplitude here. Okay, positive amplitude. And at t by half, actually t by 2, you look at t by 2, again it becomes minus a. So if I actually try to visualize this motion with a simple pendulum, so I have simple pendulum over here. So the motion starts with maximum displacement. So it starts from here actually. Okay, so let us say this is a. So it starts from here. When t is equal to 0, the pendulum is here. Now when so t is equal to 0, so by t by 4 it will come to the equilibrium point. Okay, this is equilibrium point. So by t by 4 it will be here. Okay, then another t by 4 it will go to the another extreme, like extreme on the other side. So this will be t by 2 here. T by 4, T by 2. Now when it comes back, so it comes from here at equilibrium T by 4, then it goes further to this. Okay, so let me see up to this T by 2. Look here, at T by 2 the displacement should be maximum again, but on the other side, look this t by 2. This is the t by 2. So there is displacement is a by 2. So now let me see the options here. What is there at t by 4 and t by 2? Then we will analyze this simple pendulum again. So at t by 4, the speed is maximum, it is said. Speed is maximum. We know from our discussions like previous knowledge, we know that the speed will be maximum at the equilibrium position. Okay, speed will be maximum at the equilibrium position. Okay, here the displacement is 0. Okay, displacement is 0, but speed will be maximum. Okay, and kinetic energy will be maximum at this place, t by 4. So this is the equilibrium. Okay, so this is actually equilibrium. This position is equilibrium, t by 4 is equilibrium position, and there the speed will be maximum. This is true. I hope students you are able to understand this. Now when it goes, see at this equilibrium, it is not going to stop here, right? Because the speed is maximum. Then it will go to the other extreme. So this is actually minus a, the displacement. Okay, maximum displacement here on the other side. So here actually speed will be 0, but force will be maximum in the other direction. Okay, maximum potential energy will be maximum, kinetic energy will be 0. So these are the points. Now let us see what it is said here. The potential energy is equal to the kinetic energy of oscillation at t is equal to t by 2. This is not possible because it is at the other extreme at t by 2. So if it is at t by 2 on the other extreme, then you will have maximum all the energy to be potential energy. There will be no kinetic energy because speed is 0 here. Speed is 0, so no kinetic energy. So the whole energy will be potential energy. So potential energy will be equal to kinetic energy at t is equal to t by half. This is not correct. Okay, so far it is okay. Now look, I had drawn half of the motion. I'll now draw the other half. Now see at t by 2, at t by 2 it was here. Now it will start moving this way. So t by 2 plus another t by 4. Okay, so it will be at equilibrium. So it is actually 3t by 4. It will be again at the equilibrium. That means displacement will be 0. Look there, see this position. This position is again it is at the equilibrium position. The speed will be maximum, kinetic energy will be maximum, but force will be 0, displacement will be 0. Let us see what is there. So the force is 0 at t is equal to 3t by 4. It is absolutely correct because it is again at equilibrium. This is again at equilibrium. So the pendulum is again at the equilibrium. So obviously the force will be 0 at equilibrium because displacement is 0, and we know force is a force for a simple harmonic motion. Force is having an expression F is equal to minus kx. So it depends on, it is actually proportional to the displacement. Okay, proportional to the displacement. Now what happens at t? So at t, that means when it is t, see t means again it has come to here, it has reached here. From where it started, it has reached here. So this is actually t is equal to t. Okay, capital T. So a complete rotation, like complete oscillation is happening when it reaches back. Okay, reaches back to this position. So at this position at t is equal to 0, sorry, t is equal to t, what is there? Now it has maximum displacement, it has maximum force, or the, yeah, it will be acted upon by maximum restoring force. So those things are there. So the acceleration is maximum at t is equal to t. Acceleration is maximum. Yes, because force is maximum at this position. And see, what is acceleration? Acceleration is equal to minus k by m into x. That means, you know, the acceleration is directly proportional to x with a minus sign. So wherever the displacement is maximum, the acceleration will also be maximum. So this is also true. So at extreme, acceleration will be maximum. Yeah. So these are correct. So this 1, 2, I'm sorry, this is 2 actually. 2, this is 3, and this is 4. So 1, 2, 3, first 3 are actually correct. Okay. So this option 1, 2, 3. I'm sorry, 1, 2, 3. Option C is correct. 1, 2, 3. Really, it is correct. So option C is correct. Okay. So let us go to the next problem. So this problem says, when the temperature of a metal wire is increased from 0 to 10 degrees centigrade, its length increases by 0.2 percentage, 0.02 percentage. The percentage change in its mass density closest to what? So first of all, we have to understand what is this percentage change. Then we have to see mass density means rho is equal to m by v. Sorry. Mass density is m by v. I have to find out the percentage change. That means, you know, this is delta rho by rho. So, you know, in the error, like in the first chapter itself, where you learn various type of error, we do percentage error also. You have to multiply 100 with the modulus. Okay. So this will be actually percentage change. Now here also I have to do the same thing. So since it is a constant, mass is constant, there is not going to, like, mass is not going to change with the temperature. So it will be delta v by v into 100. So this will be actually percentage change. Okay. So how to find out this delta v by v? This is actually our problem now. So what is given? See, length increase is given. See, if I write volume, in case of volume, you know what, if you are giving, like, hitting an object, how volume changes with temperature? V is equal to V0 1 plus gamma into delta T. This is the change in the temperature. Okay, so from here, look how I can write this V minus V0 divided by V0. Okay, is equal to gamma delta T. What is this gamma? Volume expansion coefficient. Volume expansion coefficient. Delta T is the change in the temperature. And see, see V minus V0, this I can obviously write delta V by V0. Now if I want to multiply 100, then I can multiply gamma and delta T into 100. But gamma is not given here, right? What is given is actually linear percentage change in the okay. Let me just tell you what is given. Percentage change in the length is given. See, delta L by L into 100 is given. So this is what is given. So how do you get this thing? See, for a linear expansion, we know this is L is equal to L0 plus alpha delta T. So from here, look, I can write delta L by L0 is equal to alpha delta T. You might be thinking why I'm writing directly this thing, how I am able to write. Look, I'll just tell you here. This side is L, fine. This is L0 plus L0 into alpha delta T. This is what I'm doing. So L minus L0 I'll bring here. Okay. Then L0 into alpha delta T. Now alpha into delta T is equal to, see, this I can write as delta L0, delta L by L0. So delta L by L0 is equal to alpha into delta T. So if you multiply 100, then it is fine. So you'll get 100 over here. Okay. So this thing is given. This particular part is given. So alpha delta T, if you look the question, this is 0.02% is given. So 0.02% is that much. Okay. So alpha into delta T. Now I have got one thing here. Alpha delta T is equal to 0.02%. Okay. Now I have to actually calculate delta P by V into 100%. Okay. This I have got gamma that is the volume expansion coefficient into delta T. So this gamma and alpha, they have a relationship if you remember. So that I can multiply here. 3, I'm sorry, gamma is equal to 3 alpha. So I'll put it here, 3 alpha delta T. See, I have already alpha delta T known. Alpha delta T is already given. So 3 into 0. So this is in percentage, 0.06 percentage. Okay. So let me see the options. Yes, this is correct option. So I hope guys you have understood this. Only trick was that you have to write 3 gamma is equal to 3 alpha. So that is the point which is actually governing the whole numerical problem here. Okay. So all right. Now let us go to the next problem. This problem is also very interesting. You look, this is from capillary rise. A capillary tube made of glass of radius this small r is given. Dipped vertically, a capillary tube made of glass of radius 0.1 millimeter, 15 millimeter is dipped vertically in a beaker filled with methylene iodide. Okay, so this methylene iodide, the surface tension is I'm sorry. So look this 0. So surface tension is Newton per meter. Okay, and density is given rho 667 kg per meter cube. So these are the known term here. And okay, so let me start again, like read again from starting. A capillary tube made of glass of radius 0.15 millimeter is dipped vertically in a beaker filled with methylene iodide whose surface tension is 0. 0.05 Newton per meter, and density is 667 kg per meter cube, which also rises to a height h in the tube. It is observed that the two tangents drawn from liquid glass interface, that is from the opposite side of the capillary, makes an angle 60 degree with the another one. Then the h is the height that is um, uh, that is closest to what of these four options. So here, just by seeing this capillary action and this particular angle, you should not jump and do the calculation with the formula this itself. Suppose this is actually some formula putting problem only with a little trick. So you know 2t cos theta by rho rg. G is the gravitational constant. I'm sorry, acceleration due to gravity. Small r is the radius of the capillary, and rho is the density of the liquid. T is the surface tension of the liquid. Okay. Now here one trick is given that will write. Let me write this on this side, single side. Okay, look here what is given in this problem. Just a small trick. Instead of giving the okay, so look here, the question is see given the two tangents drawn from liquid glass interface. See, this is liquid glass interface, so that will be liquid glass interface, that the tangent will be always toward into the liquid. Okay, so one tangent is meeting here, another tangent from the other side, see opposite side of the capillary, it is meeting here, and this particular angle is given as 60. So this angle is 60. Now we will be able to find out that this angle, which is the angle of contact is actually the tangent drawn at the glass and solid interface when the tangent is taken inside the liquid. That is actually, so the angle between the solid surface and the tangent, yeah, so a tangent at the point of contact. Okay, so now if this is 60 degree, this is 60 degree, it can be shown that this is becoming 30 degree. Okay, so you know the angle of contact is here is not 60. This point has to be remembered. Okay, so here angle of contact is actually 30 degree. So now you have got all the informations which you require to find out the height. Okay, now just a calculation. So I'll put it here 2s cos theta by so 2t cos of theta. See, cos of theta is here how much? So 30 degree, cos of 30 degree is half, I'm sorry, root 3 by 2. So this is the formula actually. Now you can just put it here. Cos theta is root 3 by 2 cos 30, root 3 by 2. 2t, t is, so t is given as 0.05 Newton per meter. So 2 cos theta and t we have written in the numerator, denominator. Six, 7 is the row. So guys, you can actually put the values. Capital A 0.1, this is millimeter, so I have to make it meter. And G I have to multiply 10 again. Then if you do the calculation, this very simple calculation, you will be actually ending up with 0.665 or something, or we can write as 0.875. Sorry, 87, 0.087, 0.0865. So it will be 0. This will be 0.087. Sorry, this is centimeter. Okay, so this is the answer, guys. So here, what was the tricky point? Tricky point is that angle of contact, finding out angle of contact. Okay, now we'll go to the fourth question. So the fourth question says a heat engine involved with exchange of heat are given here. See, the heat exchange is happening for a heat engine is this positive 1915 joule, negative negative 40 joule, then again positive 125 joule, and minus q joule. During one cycle, achieving an efficiency 50%. The value of q is what? See, in case of calculating efficiency, what we know for heat engine, this will be actually work output. This is heat supplied into 100. So this will be actually efficiency. So that is given on the right hand side. I can write half because 50% is. And see, to find out work output, we know, see, if you have a heat reservoir at T1 temperature and it takes some Q1 heat, then it does certain work done. Okay, does certain work done, that is Q2 minus Q1, and then goes to the destination, that is actually the sink. It has very low temperature. In the other sense, not low temperature. In the other sense, you can say it is actually having infinite capacity to accommodate charges. Not charges, the heat, infinite amount of heat. Actually, this is called reservoir. This is called sink for Carnot engine. Okay, so here in this given problem, whatever positive heat you can see, those are actually the heat supplied. Okay, heat supplied are this. These are heat supplied. And what about work done? See, if you add the positive ones, and then sorry, 40 minus q joule. So this is actually work done. Okay, this is work done. Now this is actually giving you, so this is 1040, and this all will see, let me just check from how the 1030. Okay, 1030 minus 1040 minus q minus 40 q, so 1000 minus q actually. I hope you are understanding this. I'm actually adding all the heat here in the numerator, all the exchange heat, then I'll get the work done. So this is this much minus 40 minus q. So minus 40 means this will be 1000, right? Sorry, I think, oh, it has gone. Let me write once again. So you have minus 40 minus q joule divided by 1915 plus 125 joule. This is then 1000 minus q divided by 1040 joule. Okay, so you just So this is for half. So this by 2 is equal 2 is equal to 100 minus q. So q, if I bring this side, this will be 5, 20. This is 1000. Okay. So 1000 minus 520. So what will be the answer here? Okay, let me check. I think this is not the answer. Let me just do once again. So work done is here actually minus 40 minus q. Okay. So this is actually, so this will be 1000 only. I'm sorry, here this will be actually, yeah, this is fine. Minus minus, all right. Okay, I think I'll just skip this because this will be answer. Somehow calculation is not coming that. I'll just come back with this later. Let me discuss this then. A charge Q is distributed over two concentric conducting thin spherical cell. You can see that this is spherical cell having inner radius small r, capital radius, outer radius is capital R. Okay, so R is obviously greater than small r. If the surface charge densities on the two cells are equal, so on the two cells, like say one at this surface, sigma 1, if at this is sigma 2, then sigma 1 are given as sigma 2. electric potential at the center, common center we have to find out. Okay. All right. So in this case, let me just consider one thing. Once the whole charge Q is given, the charge will be equally distributed since the surface charges are surface charge densities are same. So I can say Q1 plus Q2, that is becoming the total charge. What is Q1? The Q1 is the charge distributed over the smaller cell, okay, radius on surface of this smaller radius, and Q2 is actually distributed outside. Okay, so this total charge is distributed in in the cell. Okay, now the question is sigma 1 is equal to sigma 2. So from there actually I can find out something, but anyway now if I have to find out the potential, so in the expression for the potential what we have, potential is, see, if I say Q1 is the charge, then KQ1 by R, and for this also I can write the potential will be additive, obviously. Q1, this is Q2 by capital R. This is what we will say. But now what is Q1 and Q2? You have to express them in terms of sigma and capital Q. So that is the tricky part here. So look here, we know sigma 1 is equal to sigma 2. That means what? That means we know sigma 1 is equal to Q1 by 4 pi R square, and this will be Q by 4 pi. Sorry, Q1. This is Q1 by this, and sphere, second sphere has charge Q2, so Q2 by 4 pi epsilon naught capital R square. Okay. So how do you actually get, see, at this place, this is one equation, this is equation 2. See, from here if I find out Q1, so what will be the Q1? Q1 will be in terms of Q2, I can write that this is Q1 is equal to Q2 into R square, sorry, R square, small r square divided by capital R square from here. Okay, so if I put it here in the equation 2, what I'll get? I'll get Q2 R1 square, sorry, R square divided by R square plus 1. This is equal to Q. So this means Q2 is equal to Q square, sorry, R small r square capital R square divided by R square into Q. This is Q2. Okay. I'm sorry, this is actually just opposite. So if I put the value from here, if I put the value of Q1 in this equation 2, then actually I'll be getting what is Q2. So similarly, if we go from here, say Q1 by 4 pi q2 by 4 pi capital R square. So 4 pi goes off. I have to actually replace q2 by q1. So you look here what we are getting. q2 is equal to q1 into R square divided by this. Okay, now put it here. q1 plus q2 is equal to q1 plus q2 is equal to q. Okay, so we have already got q1. So I can actually q2 we have got. So q1 will be obtained. So this is how you have to actually calculate, say, q minus q2. So q minus q2 is actually q1. No, I should not bring again q1. q2 I had already got. So that thing we have to write. R square divided by R square plus R square into, so it will be actually R square divided by R1, sorry, R square plus capital R square. This is the value of q1. So if I know q1 and q2, then we'll put it, see, after we get this q1 and q2, we'll just put them here in this equation. Okay, I'll just show you the in the next page. So what we have got so far, so we have got q1 to be equal to R square by R square plus R square into q. Okay, the second thing is q2, that is capital R square divided by, so these two we have got now. Now it will be easier to find out. V is equal to, okay, q1 by q2 by R2. Now I'll put the value of R1 and R2, and finally what we should get actually, that is q into, so this is actually the answer. Okay, we have just put the values here. this. Okay, so let us go to the next problem. So this problem says, so I think here this option is correct. What we have got is this one. First option is correct. So what was the point here to note? You had to actually find out what are the charges on the smaller, like say like the smaller surface and the outer surface, or the bigger surface or bigger cell. What is the charge on the smaller cell and on the bigger cell, conducting cell? So that is what we had to find out first. Okay, now the sixth problem is said, see this problem says a 10 microfarad capacitor is fully charged to a potential difference of 50 volt. After removing the source voltage, it is connected to an uncharged capacitor in parallel. So there was initially a charge C1 say, which was charged, fully charged, and then fully charged up to 50 volt, and after disconnecting this, when it is full charged, then I connect with another capacitor in parallel. Okay, this is what I do now. This is C2, this is unknown capacitor here. Now the potential difference, common potential difference is given actually. Okay, common potential difference is given is 20 volt. Okay, what is the capacitance of the second? See, in this case, whenever this is actually redistribution of charges. So whenever there is a case like this, a capacitor is fully charged and then disconnected and connected to some other uh, capacitor in series, like in parallel, then what you need to do is this. See the common potential V common potential, we know C1 V1 plus C2 V2 divided by C1 plus C2. Okay, so here let us say this is C1 and C2, initially it had zero voltage, so this is actually zero. You will have, so C1 V1, C is given, V1 is given. Okay, and this common potential is also given. Let us just do this. See, 50 common potential, 50 volt is equal to C1 V1, that means 10 microfarad into 10 to the power. Then you have C1 V1 divided by C1 plus C2. So C2, we know C1. Then let me write C1 plus C2 is equal to, okay, this is in microfarad. Okay, microfarad only we are calculating. So 50 volt and This is actually C1 plus C2. C2 will be C1. What is this? I see, that is common potential is becoming actually 20. Okay, so not 50. So this is becoming 20, and C1B, I'm sorry, this is actually C1B1. C1 is 10 microfarad into V1 is 50. This is what was there. This has dimension CV, dimension of charge. Okay. Now look, it will be all right. So if you do the calculation carefully, what you are supposed to get, you'll get from here. So this is 10 microfarad, this is into 50, 10 microfarad into 50, so 500 microfarad divided by 20, sorry, 20, I'll bring it here. I'll keep only this here, 10 microfarad, and then take this. This was already, sorry, this was already there. This will be actually 15 microfarad. Okay, so this is the answer. So this is very simple problem. So I'll stop it here for today. Next day we'll take the rest of the questions from this part. This is actually from evening shift, 2nd September 2020 paper. Okay, bye for today.